Hello everyone, my name is Walter Zimmer and today I'll present the core contributions of our paper towards Vision Zero, the TUM traffic accident dataset. A US study shows that 51% of crashes occur at intersections, causing 28% of all fatalities. There's a Munich intersection, the driver turns right on green, but must watch for cyclists and pedestrians in the bike lane. As the driver begins turning, a pedestrian crosses the street. The driver must yield, but the pedestrian is occluded until the last second. Fortunately, we have a test field in Munich that monitors all the traffic participants. It can detect occluded pedestrians early and warn the drivers via text communication. Roadside sensors have many advantages. They have no occlusions, much wider field of view, longer range, and higher compute. Such dangerous scenarios are very common and often end tragically. Watch the green van, for example, here on the highway. A van broke down and most vehicles overtook safely, but one car, highlighted in red, approached at 180 kilometers per hour, hit the guardrail and then crashed into the van. 2 people got injured here. Here are more examples that we recorded, labeled, and published. In total, 48 accident sequences, each 2 minutes long, with 2.6 million labeled vehicles. So global road fatalities have stagnated for 25 years at around 1.2 million deaths annually. Traffic crashes are the leading cause of death for ages between 5 and 29, and one person dies every 26 seconds. The EU aims to halve fatalities by 2030 and achieve Vision Zero by 2050. Autonomous driving can improve safety and efficiency, but relies on robust 3D perception in challenging and rare scenarios. This work focuses on creating a real high-speed accident dataset. And next I'll show you how we used the A9 digital test field to create it. We first built a 3-kilometer long test field near Munich with 8 roadside units and over 80 sensors, including cameras, lidars, and radars. We then developed 3D perception models to detect traffic participants in camera and lidar data, and finally created a digital twin of the traffic. Our infrared 3D model fuses camera and lidar data and improves the detection by 1.6 MAP and runs with 22 frames per second. After we have obtained the digital twin with all the trajectories that you can see in the first row, we apply 2 models, a rule-based model using the speed and distance thresholds, and a learning-based model that was fine-tuned on our custom dataset. The rule-based model extracts features like the lane ID, the distance to the neighbors, and the average velocity. It detects events like stopped vehicle, traffic jams, and accidents. The learning-based model is a 2D object detector like YOLO. It was pre-trained on a public accident dataset and then fine-tuned on our custom dataset. We then apply mono.3D to obtain 3D boxes, track IDs, speed, and confidence scores. We evaluate both approaches. The rule-based approach is much faster, while the learning-based approach achieves higher one scores. So once accident sequences are detected, we refine the labels using our 3D bounding box annotation tool to finalize the dataset. Next, I'll show you 3 accident examples from our dataset. Focus on this blue van here. On a windy highway, a van with a trailer tips over due to strong wind gusts. And the driver was slightly injured. Another accident happened during this traffic jam on the right. A driver was speeding and got distracted. He swerved to the right and hit 2 vehicles, causing one to spin 360 degrees. Here's another one, a vehicle fire on the highway shoulder. A van stopped on the shoulder and caught fire after 10 minutes. Some people tried to extinguish the fire, but failed. Overall, the dataset includes 48 2-minute-long videos with 2.6 million labeled vehicles and 2,000 kilometers of tracks, and the longest track ID is 2.1 kilometer long. Contains around 112,000 camera and LiDAR frames, many with 50 and more labeled object in dense traffic scenes. In summary, the main contributions are the following. We create an excellent dataset with over 2.6 million labeled objects. We develop a new hybrid accident detection architecture and demonstrate the real-time feasibility of accident detection on the A9 test field. In the future, we want to integrate vision language models for scene understanding, develop even further algorithms for real-time accident detection, and expand more on detecting edge case scenarios. Advancing 3D perception edge cases brings us closer to a future where autonomous driving saves lives and reduces congestion. Thank you.